Hello and welcome again to my Physics Online video lecture series. Today's video we're going to be talking about a capacitor in an AC circuit. So basically what happens when you apply a sinusoidal signal to a capacitor. To do this we should recall first and foremost just what it is that the AC signal should look like. So recall that our AC signal varies sinusoidally. Thus the current looks like some peak current value I0 times the sine of omega t. The voltage is also going to vary sinusoidally but with some phase shift. We might recall, for example, what happened when we looked at an inductor in an AC circuit. Thus, if we have a resistor, the phase shift tends to be 0 degrees. If we have an inductor, the phase shift tends to be plus 90 degrees, or more appropriately, plus pi over 2 in radians. Reminder that radians is sort of the preferred unit to work in here, but you could convert to degrees if you'd like. You'll also recall that we introduced the idea of reactance and actually another idea, impedance, that is related to it. Let's just stick with reactance for now. There's inductive reactance. There's also going to be capacitive reactance, and the definition for the reactance is it's how much is the ratio of the peak voltage to the peak current. For an inductor, this reactance is actually given by the angular frequency omega times the inductance L. For what it's worth, for a resistor, there's not really any difference between reactance and resistance. Put differently, this means that the ratio between peak voltage and peak current does not depend on frequency if you're just looking at a resistor, and it depends linearly and you could say direct proportionality with frequency if what you're looking at is an inductor. So today what we want to do is now consider capacitors. As we did with the inductor, what we want to consider is the loop rule, or if you'd prefer, the Kirchhoff voltage law for this simple circuit in which you've applied an AC signal to a capacitor. The loop rule basically is going to say that the delta V and the delta V capacitor should add to 0. Essentially, if we drop the deltas, this means that V is equal to whatever the voltage for a capacitor is. So recall that for a capacitor, the charge stored by the capacitor is equal to the capacitance times the voltage drop across the capacitor, or in other words, that the voltage drop across the capacitor is the charge stored divided by the capacitance. So we could write here that V is equal to Q over C. So we have a Q over a C. We also might recall that current is defined as rate change of charge, so dq dt. Okay, what this essentially means is that we can write that Q is equal to the integral of I dt, and remember that this AC source is putting out some current. I is equal to I0 times sine omega t. Thus, Q is the integral of I0 sine omega t dt. Or in other words, Q is equal to negative I0 over omega times the cosine of omega t. So that gives you your charge at any given time, given maybe some initial charge parameter. Now if we combine these two equations, V is Q over C and Q is negative I naught over omega cosine omega t, what we end up getting is that we can basically just write that the voltage drop across the capacitor is given by negative of I naught over omega c times cosine of omega t. Now there's a couple of points that we might use here. First of all, we expect Vc to look like V naught times some sine of omega t plus phi naught. So what does that mean? Or phi naught c, I guess I could say. What does that mean? Well, that means that V naught for the capacitor must look like I over omega c. You'll notice that I didn't include a minus sign here, and that's because I can include it within this phase shift. To get the minus sign into the phase shift, what you have to do is, instead of adding pi over 2 here, you could subtract pi over 2 here. So phi naught is equal to negative 90 or negative pi over 2. Alright, so writing those equations out again, for a capacitor, given a current of I naught sine omega t, we expect to see a voltage for the capacitor of V naught times sine of omega t minus pi over 2. And we can write here that V naught is equal to I naught over omega c, or in other words, that V naught, or V naught c if you will, over I naught is equal to 1 over omega c. And so this, by definition, this term has to be the impedance, the reactance for the capacitor. It's also the impedance that would be present if the only thing in your circuit is capacitive elements. Impedance usually refers to the whole circuit's equivalent, maximum voltage to maximum current, for what it's worth. So the capacitive reactance is 1 over omega c. Now when I talked about inductors in a circuit, an AC circuit, then I kind of summarized by giving the two key results, namely the phase shift and the reactance value. So we can do similar here by noting what the phase shift is and by noting what the reactance is. So in some sense, we could put a little box around this equation if we'd like. Put a little box around this equation. These are sort of the two key results in some sense as equations. What are they here? Again, we have the phase shift. Phase shift is saying that the current leads the voltage by pi over 2 or a quarter cycle, or in other words, that voltage lags current by pi over 2 or a quarter cycle. You could put that simply as phi 0c is negative pi over 2 rather than plus pi over 2. So that is our phase shift result. Our other result is the reactance. So we have now capacitive reactance, and the capacitive reactance is basically telling us that the ratio of the peak voltage to the peak current for a capacitor. So chi c, again defined as ratio of peak voltage to peak current. For the capacitor, this capacitive reactance is 1 over omega c. Thus, it is also frequency dependent, but now it is inversely proportional to the frequency. We can summarize our results by way of table. Essentially, what we would have is the device type, so resistor, capacitor, inductor. We could have the reactance, that is the C, or capital X if you'd prefer, term. And then we have the phase shift. The phase shift, of course, is your phi naught term. And again, the equation for that is by way of if I is I naught sine omega t, then the voltage drop for this device will be V naught sine omega t plus phi naught. Okay, and so we can basically make this little table that shows each of these things. For the resistor, the reactance value is just the same as the resistance. In fact, we basically don't talk about resistive reactance. We just usually say resistance. The phase shift is 0. For the capacitor, we have capacitive reactance, and that is 1 over omega times C, and we have a phase shift of negative pi over 2. For the inductor, we have an inductive reactance, omega L, and the phase shift is now plus pi over 2. Basically, you could call these things as how are the voltage and current related as far as leading and lag. So if the resistor, the voltage and current are synchronized, neither one leads nor lags. For the capacitor, the voltage is going to be lagging the current, or if you prefer, the current is going to be leading the voltage. And for the inductor, the voltage will be leading the current. Or if you'd prefer, you could also say that the current lags the voltage. And there's actually a little mnemonic for these two. Remembering that resistance, you have synchronization. The little mnemonic that you can use is what's called Eli the Iceman. Basically, this name, Eli, remember that E is E field, but that's the same as a voltage. So for an inductor, which is an L, the voltage leads the current. For a capacitor, the C, the current leads the voltage. So Eli the Iceman, Eli, because the E and therefore the voltage comes before the I in that word, or before the current, the voltage leads the current for an inductor. For ice, the Iceman, the current I is first, the voltage, or E field E, is last, and so the current leads the voltage in a capacitor. So that little mnemonic should help us to remember what the phase shifts are for the capacitor and the inductor. As our example of this, let's consider a capacitor that has a signal being applied to it and determine the capacitive reactance, and then also how much current was needed to provide a given peak voltage. We've been given a capacitance of 2.4 times 10 to the negative 5 farads. We've also been given a frequency, again lowercase f, of 1.6 times 10 to the 3 hertz. Remember that omega is 2 pi times f. So for this first part, where we're trying to figure out what the capacitive reactance is, this should be 1 over omega times c. This is also 1 over 2 pi times f times c. So if we want to plug the numbers in that we've been given, we have 1 over 2 pi times 2.4 times 10 to the negative 5 farads times 1.6 times 10 to the 3 hertz. All of that can go into your calculator. What you end up getting is about 4.144659976. Now, do you remember what the unit is from our previous video for the capacitive reactance? I will round that off. You might pause the video before I write the unit down and try to remember what the unit is. Alright, so if you paused it, then you already have figured out what the unit is. If not, the unit here is ohms. It's the same unit as what we had for resistance. Second part of the problem, and I'll switch colors here for the non-colorblind. I'm going to figure out how much current is needed to get a peak voltage of 12 volts. Well, remember that this capacitive reactance is defined as the voltage divided by the current. And so if what I want to know is how much current I'm needing, that means how much current is going to be peak voltage divided by capacitive reactance. So I'm given 12 volts. Again, this is the V naught. The current in this case, peak current, is I naught. So I have 12 volts divided by 4.1, etc., 4.1446 ohms. If I plug that into my calculator, 2.895, so let's round that to 2.9, but 2.89529,179 amps. So we've found for ourselves a needed peak current in amps. We found for ourselves a reactance in ohms. And that is all that I'm going to do in this example, and thus that's all for today's video. Hopefully you learned something from it, and as always, thanks for watching.